let's talk about energy. This class is about energy, and so let's get started with some baseline concepts about this. We'll be pretty much looking at energy the entire course, and so we'll be learning it every day, but let's sort of get a start on this. And so here the textbook starts with some definitions, and so let's do that as well. And so let's fire up some slides. And so again, we're looking at work and energy, how these two things are related. And so work will be something we're going to define, and again, trying to learn more about energy. So just first thing, energy is one of the richest and most productive ideas in all of physics and all of science, actually. So it's super important. We're going to spend lots of time talking about it. But one warning is it's actually pretty subtle, right? I think there's a lot of physical concepts that are maybe easier to kind of wrap your head around than energy. An example would be a force. Most people are able to get the idea of a force, something that pushes or pulls, right, pretty quickly, where energy is a little bit tougher. Now, one thing we're going to keep coming back to, which is a really important thing about energy, is that it cannot be created or destroyed. It can only be transferred. And so we're going to look at some examples of when it can be transferred. And just to kind of give you a sense of what I mean of how energy is pretty subtle, this is a quote from a famous physicist, Richard Feynman. You may have heard of this guy before. It is important to realize that in physics today we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It just doesn't work that way. However, we have formulas for calculating some numerical quantities, and when we add it all together, it will not change except for energy going in and out. Again, energy can't be created or destroyed, but can be transferred. And it's really important too. Here's one of the premier physicists and saying basically we don't really know what it is, right? It's sort of a weird, fuzzy concept. All right, but luckily you do know a good deal about the transfer of energy in daily life. And here's just some examples, right? You ingest chemical energy, maybe from a sandwich, and use it up when you are active. You put electrical energy into a toaster, and the toaster raises the temperature of your bread. And then you compress a spring, maybe in some toy, like a toy gun, and the energy stored in the spring can launch a ball. These are all examples of energy, but also energy transfer. So this happens all the time, and we're seeing it all the time. So that leads us to our fundamental definition of energy. Energy is the capacity to do work. And we're going to talk about this, but just, in kind of a rough sense, this makes sense, right? It's hard to get work done when you're wiped out. Work makes you tired. You've used up your energy. So that's sort of the rough idea, but in physics we have a more precise definition. And so we're going to sort of look at that now of what we mean by work. And work is defined as the product of the force exerted on an object and the distance the object moves. For us, we're always going to focus on forces that are in the same direction as the motion. This doesn't always happen, but it covers a lot of ground. Now, one thing is we're going to kind of hit on this. Work is only done when the force succeeds in moving the body that it's acted on, right? So again, our equation is force times distance. It has to have some distance that it moves. Just some notes. We won't really talk about things other than this, but just keep in mind that this equation only works for a force that doesn't change, that's constant. And again, it's only true when the force is in the same direction as the displacement. And like we said, to do work, you need two things, a force and a motion. Now, we look here at our units, and we'll talk more about this, but for work, our unit for force is going to be called the Newton, after Isaac Newton, N, and then our unit for distance is the meter. So we get force times distance. So Newton times meter is going to end up with a unit called the joule. And so that's going to be our fundamental unit of energy. All right, so here's some examples. Here's Yu Darvish of the Padres. And what is he doing? Well, he's applying a force on a baseball, right? And so what does he do? Well, by doing this, he transfers energy from his body to the baseball. And this is going to be a kind of energy that we'll talk about called kinetic energy. And so by doing work on the baseball, by applying a force on it and moving it some distance, it's hard to draw that, but he's going to move this baseball a distance, he's going to increase its kinetic energy. and decrease his own energy from his muscles. Another example, here's someone lifting up a box. And in sort of a same sort of idea, what they're doing is they're taking energy from their muscles, they're applying some force upwards, and what do? Well, they lift the box up, some distance, roughly something kind of like this here. And so by lifting the box, they're able to increase what we call the potential energy of the box. And what that means is, if in this last picture here, if this person was to drop the box could land and it could destroy something, or it could transfer energy to something else, right? And so basically he was given that energy, that potential, that stored energy when the person lifted it up. But in both cases, right, this and the baseball, work was done. It was done as force times a distance. So you have to have both of those. Here's things about work. Again, you have to move the object to do work on the object. And so, for instance, if I hold up a dumbbell but it doesn't move, I do no work on the dumbbell. Now, my muscles are doing work. They are transferring energy. If you were to look at my muscles and measure them, they'd be warmer, hotter than they were before. And so in that case, I'd be increasing thermal energy. But by this very specific definition of work, I wouldn't be doing any work. And so this, again, just comes from what our definition of work is. And another curious thing is if the force is perpendicular to the motion, it doesn't do any work at all. Again, we won't really talk about that, but just kind of interesting thing to discuss. All right, so back to units. So in physics, we primarily use what's called the System International units, which I'm going to just always call SI units. And so these are the ones that are used more in Europe. Unfortunately, we don't use them all the time here in the U.S., but in physics classes, we'll be using them. And so if you look at different things we measure, like, for instance, position, the SI unit is the meter. And we'll use M for that. Velocity, which is just a fancy way to say your speed and the direction of your speed, is going to be in meters per second, which again we'll write as M over S. Then we have another sort of fundamental, which would be mass, and in the SI we'll use kilogram for that one there. And pretty much we can build up every other unit in the SI system from these ones here. But I just wanted to kind of make you familiar with some of the basic ones. And of course, I guess the last one we should put in would be time, which would be seconds. Okay, so let's look quickly. We won't talk a ton about this in the course, but it's probably good just to review what a force is. Again, a force is some kind of a pushing or pulling agent. And just some examples here, gravity exerts a downward force on you. If you bounce a ball off the floor exerts an upward force on a ball during the bounce. If you're in your car seat and you put the gas pedal down and accelerate your car, the seat applies a forward force on your body, right? So there's just a bunch of different examples here of cases where a force is being applied. Now, forces have direction, and so we can look at sort of how forces are applied if there's more than one. So here's an example of two forces that are in the same direction. What they do is they add up to be a bigger total force, and so we say that the forces add. Now, you could have those two forces going in opposite directions, which happens all the time, and those forces cancel, and so the total force is 0. And so there's different kinds of situations that can apply depending on how the forces are applied. And when the force is not 0, so by net force we mean sort of the addition of all the different forces, when it's not 0, the force will experience an acceleration. And by acceleration, in this particular case, sort of a simple way to think about it is that your velocity is going to change. And so in a simple case, like we were talking about that car, if you put the acceleration, if you hit the gas pedal, your car will accelerate. It will start at 0 speed and will get to larger speed as time goes on. And the equation that sort of tells how this happens is F equals ma. And so you've probably seen this. F equals ma, and one thing you can do is solve this for A, force divided by the mass of the object. And so if I apply the same force on some object, the acceleration will sort of be this sort of battle between the force and sort of how big the mass is. And so, for instance, here we sort of bring up the idea that if you hit a golf ball and a bowling ball with the golf club, what's going to happen? Well, the same force makes a small object accelerate more than it would a more massive object. And then finally, sort of circling around this idea of the acceleration, it's any change in velocity. For us, we'll always sort of focus on changes in the speed of the velocity. And so it's measured as a rate of change of the velocity. So we talked about the velocity as being meters per second. It's basically how many units of distance do you travel every second. Well, acceleration is sort of a weird idea. It's meters per second per second. And the way I like to think about it is it's kind of the speed of your velocity, if that makes any sense. And so, like your acceleration, what's happening is you're adding speed units, meters per second, for every second. And so you get this weird fraction where it's meters divided by seconds over seconds, and we just like to be fancy and write that as meters per second squared. Now, the big thing that we're going to use this for is just to kind of look at our units a little bit here. So most of that was just to kind of build up our units. So our units of force we can write as m times a. And so that's kilogram, and then we just talked about acceleration as being meters per second squared. And so that's our definition of what we call a Newton. And I'll just always write that as a capital M. And so we're sort of ready now to look at the units of work. Work is force times distance, and so that force is kilograms, meters per second squared times meters. And so work is kilogram meters squared divided by seconds squared. And of course this is what we call the joule. And again, I'll often write that as a J. And really what we're just trying to do is just get a sense of what this unit looks like. And if you look here, hopefully it makes sense that we can think about this as two different pieces. This is the Newton, and then this is meter. So Newton times meter, force times distance. And these units are just a little bit more complicated. Right. And actually, we'll define some of these kinds of energy that we've been talking about. And so kinetic energy, the energy of motion. A moving object with a mass has kinetic energy. Potential energy, we talked about this, the guy lifting up the box. This is stored energy. A couple of examples would be the gravitational energy like we were talking about. Also energy when you compress a spring is a form of potential energy. When you compress that spring, the energy is stored in that spring. And then another example of energy, again we'll be talking about tons in the classes, is thermal energy. And that's basically the temperature of something, heat. So kinetic energy, our equation looks like this. We get an object in motion has energy, we call it kinetic energy, and our equation is 1/2 mv squared. And so we can do some examples here. So like that a baseball example we were doing, if we take a baseball, baseball's mass is 0.145 kilograms, moving at 30 meters per second, which is about 67 miles per hour. So, pretty decent velocity for a non-baseball player. So 1/2 times the mass times 30 squared, and I get this number here, and I round it up to 65 joules. And so we might have questions that ask us to calculate the kinetic energy in a case like this. Here's another example. A quarter is flipped about 4 feet in the air, has a speed of reaching your hand of about 5 meters per second. What's its kinetic energy? Well, again, the mass of a quarter is pretty tiny. It's this over here. So I do 1/2 times that mass times the speed of the quarter. In this case, I get 0.07 joules. So hopefully it makes sense that baseball going at 30 meters per second is going to have much more energy than a flipped quarter. The last sort of energy we'll talk about right now is, again, potential energy. And so potential energy can be thought of as energy stored in the forces between or within objects. And so one classic case is potential energy of gravity. And so here's an example of where we move a ball up to some height of 3 meters. And so in all three cases, the potential energy of the 10 Newton ball is going to be the same. We're going to bring it up to some height of 3 meters. And again, it's potential because if I was to drop the ball from that height, when it hits the ground, it's going to be moving with kinetic energy. So you basically have this stored energy that could come out and convert to kinetic energy. And so this is the gravitational potential energy in this case, and it's energy stored in the gravitational forces between the ball and the Earth. And this energy can allow this ball here to do work. And so again, when we sort of separate this ball from the Earth, the forces themselves will store energy. So we'll see this a lot, that forces between objects can store energy. The gravitational potential energy, the equation is mgh, and I should probably just draw a g over here to be consistent. Now g is something that we haven't seen before, beg your pardon, and g is the acceleration due to gravity. And so this is a number 9.81 meters per second squared. For us, we'll sort of say it's okay to use 10 meters per second squared. And the way you think about this is the upward force when you move some object upwards with a constant velocity is this mg. Mg is basically the weight that gravity pulls down. And so if you move at a nice constant velocity, move your object upwards, the work you do is mg times the height that you push it up, mgh. And so here we have some examples of calculating this. So how much gravitational potential energy does a 70 kilogram high diver have on the 10 meter platform? Again, in this example here, we're going to use 10 for the mgh. So again, our equation is gravitational potential energy is mgh. And so here we got 70 times 10 times 10. You get 7,000 kilogram meters squared seconds squared, which to write a little bit nicer, we write as 7 kilojoules. Again, what does that mean? It's 7 times 10 to the third joules. Just a nicer way to write it than 7,000. How massive would a book have to be to have a potential energy of 40 joules sitting on a shelf 2 meters off the floor? And so what I do is we sort of do it backwards. We say m times 10 times 2. Again, our equation, mgh. And here we want that to equal 40. In order for that to work, if you use your calculator, you get 2 kilograms.